We're going to look at number 3, and 3 kind of does what I have suggested in the past, doesn't happen very often. And this isn't an AP question, so not to say that it's going to happen a lot, but they give us this table that lists atomic radii and it lists first ionization energies, and it's 4 elements. It's these 4, and they're not listed in any particular order. And then they're going to ask us a bunch of questions about them that really all of it comes down to identifying these 4. So you can see that I've listed what the 4 are here, and I'll run through how I actually figured that out. So we're going to come over here, and I just sort of listed them more or less in the order that they were up here, and we're going to do some thinking about what our prediction is for the atomic size of them. So let's start with carbon. So carbon's right here on the periodic table, and it's going to have some size of atom. Now oxygen, because it has more effective nuclear charge, the oxygen is actually going to be slightly smaller than that. So at least we know pretty confidently the relative sizes of those two. Phosphorus is down an extra period. In other words, there's a third ring. So we're expecting phosphorus to be quite a bit bigger than the other two. And then chlorine, because it has more effective nuclear charge than phosphorus, should be slightly smaller than that. But I suspect it's still going to be a bit bigger than carbon is. So that's a good basis for figuring out our orders. I think that oxygen is going to be the smallest. So I came up here and listed oxygen as the smallest. Phosphorus is going to be the biggest. I think chlorine is going to be slightly smaller than that. And then carbon is going to be slightly smaller or slightly bigger than oxygen. So you can see I matched those orders to what I was predicting over here. Now, if you're wondering, well, wait a minute, these are kind of kitty corner to each other. How do we really know? And yeah, one of the things that I'm saying is that yes, if you add an extra shell of electrons, you're going to increase the size substantially. Distance makes a much bigger difference than simply adding a couple more protons. The within a period size changes are smaller than if you go down the period. Now that we know the size, we can make some predictions. Like, for instance, phosphorus is the biggest atom. So if you think about ionization energy is the energy it takes to remove an electron. So I think that it's going to have the lowest ionization energy. And then I'm going to list them in order based on that size argument. So we're thinking phosphorus will have the lowest ionization energy and oxygen being the smallest. Sorry about the breaks here. In case you're wondering, I occasionally get interrupted when I'm making the video. So in any case, because carbon is the smallest, we decided it has the highest ionization energy, as in it's the hardest to remove an electron. And the biggest one has the lowest ionization energy. And let's see if that's true. Oxygen, which is the smallest, yep, looks like it has the highest ionization energy. And phosphorus, which is the largest, seems to have the lowest. So the trend seems to be following for all of them. Now we just need to make an argument. Alright, so I've written out an explanation here, and I hate to tell you I couldn't finish it. I just don't have room on the tablet. But let's see what I've got so far. Element number 3 is chlorine. So make a statement. They asked us which element was number 3. And so we answered the question at least. And then they wanted us to justify in terms of both properties, as in the atomic radius and the first ionization energy. So because chlorine has 3 shells of electrons, it will have a larger atomic radius than carbon or oxygen. It has more protons in its nucleus than phosphorus, so it will pull the electrons closer to the nucleus than those in phosphorus. So we made an argument for where it fits in the size chart. Then the part that I got cut off on is more or less I want to say, because it's the second biggest, its electrons are easiest to remove, and I need to convince them that I know that first ionization energy is the energy it takes to remove an electron. So because chlorine is the second largest atom, its electrons will be easier to remove than carbon and oxygen, and that's kind of where I got cut off. And we definitely want to say why, that we understand that they're further from the nucleus, so their attraction is less than the others. So I think you'd have to finish it up after this, but you get the idea. Part B just wants to know what is the outermost energy level that has electrons in element 2. In other words, what is the valence shell of element 2? Since we've decided it's phosphorus, it looks to me like the valence shell is the third valence shell, so I say so. And they want to know how many valence electrons there are. So I count 1, 2, 3, 4, 5 valence electrons. You notice they did not say justify, so I think that's all they want, and we move on. In part C, they want to know which element would you expect to have the highest electronegativity and why. we know it's going to come down to oxygen or chlorine. And this is the classic example that I think everybody worries about, which is kitty corner elements. So it turns out, just kind of how we saw when we started the logic of how to figure out what these are, that as you add a whole nother shell, that electron that you're trying to attract is much further out. Distance has a bigger impact on lessening attraction. So oxygen is going to be the more electronegative here. And, you know, I really doubt that AP would go down this route, but this review book certainly has. So oxygen is going to be the most electronegative. And I'm not going to write out the argument here. I want you to, but if you think about it, the arguments all have to do with shielding an effective nuclear charge, as in, you know, clearly oxygen's more electronegative than carbon because it has more protons in its nucleus, and therefore it pulls that valence shell in closer. There's a much stronger attraction to that valence shell. And so, you know, electronegativity, which is the drawing of electrons in a bond, they would be more attracted to the nucleus because those electrons in the bond are in the second shell, much closer to the nucleus than the ones in chlorine, which are in the third shell. So more effective nuclear charge than carbon and much closer to the nucleus than chlorine and phosphorus is the reason oxygen is more electronegative. In part D, they want to know what the photoelectron spectrum of element 4 would look like. So since we know that that's oxygen now, we just have to draw its photoelectron spectrum. And remember, binding energy goes on the x-axis. Number of electrons is what really goes on the y-axis. And when we start on the left, we're drawing the lowest energy orbital. So oxygen, its first orbital is going to be a 1s. So we draw it sort of like that. Then its 2s would have less binding energy because it's further from the nucleus, but it would be the same height. So there we go, dude. The 1s. Then we did the 2s electrons. Now we're up to the 2p electrons, and they are going to have even less binding energy because they're a little bit further away from the nucleus. And I was about to go up to 6, but clearly I don't want to do that. It looks to me like there's 1, 2, 3, 4. So we'd only want it to be about twice the height. So somewhere maybe I went too small. Anyway, you get the idea. Ooh, that's terrible. Anyway, twice the height of the others, and then we're done.